All right, so let's do the thing. So today we're going to talk about exploratory data analysis, and we'll talk about that next time too. This one's going to take at least, well, this one and next one at least. So as I said, exploratory data analysis. This is an ignored part of statistics, and it's actually really easy too, which is kind of fun because it's just making charts and graphs and stuff. So it's kind of cool. So if you're going to find out about anything about a data set, you got to understand the data themselves, obviously. For those of you not living under a rock, it just seems like it's obvious it would have to be the case. So you're basically getting a feel for your numbers. So it's easier to find any mistakes you might have made. Because none of us are perfect, so now and then you will code something incorrectly, for example. So an example, I can think of a data set of about cigarette smoking that I've played with a little bit. That a friend collected years ago. And anyway, one of the things it asks is how many cigarettes do you smoke a day? It's trying to predict how many cigarettes. It's trying to predict how many cigarettes people smoke per day without using it's not behavioral, physiological measurements. Okay, so just with behavioral stuff. So he asked people how many cigarettes they smoke per day, and reasonable numbers are anywhere from 1 to 60, 70, 80. One person wrote down 400. That is a lot of cigarettes. When you think about it, it's about 20 packs of cigarettes. That's impressive. That's Screw the Olympics, Go Pro. So at that point, maybe a mistake was made in coding it. Maybe the person typed in the number wrong. Maybe the person who took the survey misunderstood it and read it as cigarettes per month. I don't know. But it's pretty clear that that's a mistake of some sort. Right? Now, it could be a mistake of the person who filled the survey out again, or it could be a mistake of the person who put it in a spreadsheet or whatever. We don't know, but it's one you're going to look at, and we call that certainly an outlier, or perhaps. It's an odd value, and it's strange, and it makes you think maybe we should remove all that person's data. Okay. Another thing that was asked in that same survey was how old were you when you started smoking, and there was one in there that said 4. Now that's possible. You hope it's not true, but it's possible, right? And especially considering those data were collected about 40 years ago, and if that person was maybe sick, yeah, it's possible. So maybe you might keep that in, but you might want to take a little closer look at that. The guy who said he started smoking when he was 4, right? So, and frankly, it'll also give you an idea of what actually happened in your experiment. So, before you do the t-test, the f-test, all the graph, you just look and go, let's look at a graph and see if one's bigger than the other. Have a feel for your numbers. Right? So that's what I'm talking about today and next time. And as I said before I got to this slide, this is one of the most overlooked parts of statistics, and that's exploratory data analysis. This is an idea that was developed is probably a little strong. John Tukey took all these techniques and put them together and called them exploratory data analysis. Did he develop these techniques? I don't think most of them he did, but they were techniques that were out there, and he talked about this. He wrote a book called Exploratory Data Analysis. You don't just get a feel for your data, too. You also are able to generate hypotheses about your data. And that's an important thing, isn't it? That's an important thing, is generating hypotheses. Because you can look and go, I wonder why that happened. I wonder what would happen if we do this. Or if we did this rather than that, whatever the this and that are. So basically, it's giving you, again, a feel for your data, a sort of intuitive feel, not just this must be how it works kind of thing, and the stats say this, not just that. A real feel for it. And you get an idea of what happened without losing any of the richness in your data. In other words, you still have all the numbers. You still have all the numbers. At some point, you're going to want to summarize that. A big pile of numbers doesn't help anybody. But early days before you're presenting this, at a conference or in a paper, or even to your lab group, or next year when you're talking to your thesis supervisor or whatever, the first thing they're going to want to see is a bunch of just graphs and numbers. They don't want to, let's slow down on the ANOVA, slow down on the t-tests a little bit, shall we? Okay? So you can see all the numbers, but you still have all the numbers. But you get a little bit of a summary, and that's kind of what we're talking about in the next couple days. I don't know what that horrible beeping noise is. That annoys me.
I can't figure out what it's coming
Oh no, it's coming from my computer. I don't know what I don't know what's doing it. It's a noise that's annoying, and it's not actually from the speakers, which I find very strange. Because if I turn the volume all the way down, so people listening on the YouTube video of this or on the podcast, the beep, it's your computer. It's gonna die. Right. I'm sorry about that. I don't know what's. Pretend you're in a submarine. We're sending an active sonar. By the way, you know, in a submarine they never do that. The ping, ping. You know what that's doing? That's telling everybody, we're right here, we're right here, we're right. You never do that. I don't know why I care about that. One of my favorite movies is The Hunt for Red October. You ever seen that movie? With Sean Connery, he's the captain of the submarine. Yeah, so when my wife was pregnant with our daughter, when she went in for her ultrasound, I looked at the guy and I said, "Are there any sonar contacts, Mr. Kamarov?" Nothing. Just looked at me like an idiot. My wife said, "Please don't do that again," when she was pregnant with John. So I said, "I promise I will not say, are there any sonar contacts, Mr. Kamarov?" You can see where this is going, obviously. So I just said, "Give me one ping, Yuri. One ping only." And she was impressed. And the person doing the sonograph thing had no idea what that meant. So that was great. Like most of my jokes, who knows? So I got some numbers here. These are just, I don't know what these even are. Let's pretend it's a statistics test. Let's pretend it was a statistics test out of 35, and here are the frequencies of each value out of 35. That's actually not bad, except for the person that got 10. I don't like that much. This kind of relative frequency table is pretty useful. We can still see, we still know what all of the numbers are. We can get all of them. There's a 10, there's two 23s, there's 525s. See, you see what all the numbers are. We've grouped them. So we got a bit of a feel for them now. We can see that it peaks around 25. I'd like 25 out of 35. That'd be a number that would make me happy. All right. So that's the numbers themselves don't matter. The important thing is that I'm showing you that I can put a bunch of numbers together and get a bit of an idea of what happened. So what we can do is we can say, for example, we can sum the x's, that's just the scores, times the f's, the frequencies, so 1 times 10, whatever. In fact, I did that right here. So 10 times 1, 23 times 2, 25 times 5, 30 times 2, 33 times... Add that all up, that gives us 309, and we have, whoops, sorry, go back. So 309, yeah, so 309, and then we would divide by the total number of observations, that'll give us the mean, right? So we now have something, and the relative frequency histogram allowed us to do that pretty easily. You know, you could do this in your head, right? 11 plus 46 plus 125 plus 60 plus 66 plus 35. So there's that. So this is, again, all this is doing is it's allowing you to, I'm just showing you that even with the numbers themselves, if we group them, and it makes some calculations easy. And you're saying, Dave, I'm going to do all my calculations with the computer. You know, sometimes it's actually easier just to use a paper and a pencil in your brain. Like it really often is just quicker and easy enough to do. All right. Oh yeah, it's 309. And then we would divide back to the total number. 1 and 2 is 3, and 5 is 8, 9, 10, 11. So 309 divided by 12, and that'll give us the mean. Okay. We could take these and put them into a frequency histogram. So relative frequency, so what's doing it? Relative means it's showing the different values. You know how I did this? I took a spreadsheet of those numbers, and I told, I think this was the Mac program numbers, I said, make me a histogram. I don't care about the numbers themselves. I don't care about how pretty this is. I just want to look at this and see, oh yeah, it goes up here, here. This troubles me. The far end troubles me. Because if this is a quiz in one of my classes, it's test in one of my classes, and somebody got 10 out of 35 and everybody else is okay, this makes me think that somebody's in trouble. You know when I say, maybe you've heard me say this before, when I hand back tests and I say, nobody's in any trouble. And I know that by looking at distributions and go, nobody's way in, you know, crazy, not doing well. This person is. That's 10 out of 35 is not good, right? Makes you wonder if they're in the wrong class or something. You ever do that, go to the wrong class? Make you feel stupid and you just stay there because you're in the wrong class? Right? So you go into a fourth year chemistry class when you're in first year and you just sit there. I did that. Because I'm an idiot. Yeah, we've again lost no richness in our data. Well, this scale's weird, kind of wonky, 1 1/4. It just did that automatically. I can read that and get the numbers all back. I can get all the numbers back. That's nice. And so I can reconstruct a data set if I really wanted to. And I can spot oddities. And again, this one here. So I might take a look and say, something that came to 35. Well, you know, I'll tell you something. We all have bad days. Could have been just been this person had a bad day. It could have been this person didn't study properly. It could have been they thought they knew more than they did. Okay? But that would trouble me. And like I said, I look at distributions of marks in my classes whenever I give out any kind of evaluation just to make sure everything's okay. All right. This is actually my Wordle statistics. I just put this here this morning. So you could actually get, so this actually shows you that I got that one in the last, look at that, 444 days in a row, and I got this one in the very last day, last guess. You know, Wordle, the game, right? So you can actually take a look at this, and you can get my average number of guesses, right? Because we got 0 plus 32, of course 0. That's guessing it right on the first guess. Of course I haven't done that. I use the same word every day, orate. It's got 3 vowels, it's got a T in it. Anyway, we can take all these numbers, add them up, divide by, I've played 765 times, takes me 3.98 guesses. Actual data. They're useless data, but those are real numbers that I've been collecting for over, geez, about 3 years. Is that right? 65, about 2 years. 2 years. All right. Not that that matters. I saw that this morning and I went, oh, I know that. That's a relative frequency histogram. Let's show them that. All right. So if we have categorical data, before these are all not categories, they're numbers, they're quantities. With categorical data, you don't get a histogram, you get a bar graph. They're basically the same thing. They're showing relative frequencies, but there is no inherent order in the values, right? There's no inherent value, so order in the values. So there's no scale. So if you had 1, 2, 3, 4 on the x-axis, fine. But if you're doing one of these and it's hair color, you know, blonde, brown, red, black, is blonde, like is brown twice the hair color that black is? It doesn't make any sense. There is no ordering to it, right? It makes no sense that way. There's no ordering to it, but you can get a good feel for it. But you can put it in any order you want. So let's say we had a Stat 2126 class, okay? And this was, I made this slide up a long time ago, back when we taught all student statistics, not just psychology. So we would often have psychology students mostly, but we'd have sociology and CSD and biology and whatever. We'd have all these people in our classes. That's actually, those are real numbers from like 25 years ago. But let's just say we had this. We could then make a relative frequency bar graph, basically. But along the x-axis, we'd have psychology, sociology, CSD, and biology or whatever, but the order doesn't matter. The order doesn't matter. So here's here. So, like, I've got psychology over to the left because, I don't know, that's where I thought I'd put it. I could have put it in the middle. Doesn't matter where I put it, right? Here's a pie chart. I have never seen a pie chart ever used in science. It's used a lot in, well, if we want to look at sales in the last quarter, like I think it's those kind of people. And I'm calling them those people. The people who are on cell phones waiting for airplanes. Well, we have to look at the vertical integration of the deliverables and the various synergies. Whenever I sit there thinking, I'm so glad I don't do that. I'm sure they're very happy. I'm just glad I don't do that. So I've never seen a pie. You know what though? This isn't for somebody else. You're not putting this in a paper. You're not putting this in a talk. This is so you understand your data. So if you like pie charts, make freaking pie charts. Right? That's how you do this. So if you like them, you do them. Now, quantitative variables, as I said, easier. That's where we started, really. We use a histogram, of course, as I just described. What the histogram allows us to do with quantitative variables is it gives us a pretty good idea of central tendency, the middle value. It gives us an idea of how spread out the scores are. Right? How spread out the scores are, and the shape. So we can get a rough idea of the shape of the distribution. Because we put it all together, we get what's called distribution, right? So we want to get an idea of the shape. Okay. When I was a kid, and the guys were in space, like in the moon, there would always be a little beep like that every 7 seconds. Couldn't dart toad. So let's pretend I'm on the moon. This is one small central tendency for man. One giant leap for skewness. We can describe the skew of a distribution. Skewness is how moved over it is. This is called negative skew. This is called positive skew. And you're going to look at that and go, that looks wrong to me. And I know, it does. Here's a little mnemonic for you. The tail tells the tail. I feel gross just saying that. Positive or skewed to the right, negative or skewed to the left, okay? The tail tells the tail. I almost feel gross saying that for some reason. I hate little expressions. I shouldn't hate that. It's helpful and useful. It's because I didn't come up with it. That's why I don't like it. It's because I didn't come up with it. If I thought I'd be telling you how clever it was, I'd be selling merch with that on it. There'd be hats and water bottles and all kinds of crap. Anyway, look. You can even put a number on skewness. I have no freaking idea how. I can read it, but I don't know what the formula is and I don't care. Because I can look at that and go, oh, it's skewed. And it's skewed in one direction or the other. That's all I really need to know. Is that this is a course for statistics being used as a tool. This isn't a course about statistics as an end in and of themselves. So we're not going to worry about certain things. So I'm not going to worry about telling you how to, because I don't know. You can get it, who cares? But describing positive or negative is reasonable. All right. Okay, yes, it works again. We can talk about kurtosis, which to me always sounds like something you might treat outpatient. So if it's leptokurtic, it's like me. If it's platokurtic, it's like Paul Dupuis. I called Paul fat, that's what I just did. It's a joke. It's not really a joke, I'm reporting the truth, just the news. It's no fun anymore. Paul used to be a lot bigger than me, and I used to be able to call him all kinds of horrible names, and now I can't really. He looks pretty good now. He shaved his head, do you guys see that? You see, he shaved his head. It's a look, it's a good look for him. He looks kind of scary, a little bit intimidating. He looks like he should be driving like a black pickup truck giving you his advice on the COVID vaccine. If you put some dark glasses on, he'd just completely sell it. But seriously, I forget this all the time. Which is which? Kurtosis is a thing. We can describe it. There are words, and I never really care. I'm never going to ask you what. You know what? Why would I ask you? They're open book freaking tests. Oh, it's right there. That's really testing your ability to look up something you wrote down. So don't worry about it too much. Okay? But you'll see this, and there are ways to describe it and to measure it. I don't know what they are, and I don't care. They're very little use. Distribution can be symmetrical or asymmetrical. The asymmetrical ones, the skewed ones are asymmetrical. Right? They may be unimodal, bimodal. I've never seen a trimodal distribution, but I assume it's possible. Very often, when you teach, when I used to teach stat 2126, you know, the intro stats, the one you took before this, very common that the first, about halfway through the course even, that the distribution is bimodal. Don't get it and get it. Goes like this. Now, in this course, it's much more, tends to be skewed. It tends to be skewed to the left. In other words, most of you are really over here, doing really pretty well. Right? But early on in stats, intro psych as well, teaching intro, bimodal distribution is very common. Intro classes in general. People, remember in first year you didn't know how to go to school. You thought you did. You didn't really. Could be uniform. If we were looking at, let's say we had a die. We were rolling a die. Well, there's only six, again, it's a 6-sided die, not one of your 22-sided Dungeons and Losers things. I'm kidding around, I'm having a little fun. A lot of my friends play those games. I don't, mostly because I can't see things. No, let's say 6-sided die. 6-sided die. You roll the 6-sided die. You get a 1, a 2, a 3, a 4, a 5, and a 6. It's uniform. Right? Now, those are also discrete points. So that's a little different, but you know, it's just as likely to get a 1, a 2, a 3, a 4, a 5, a 6. And if you have a 20, how many is it? Having 20, 24, 22, 20, whatever, then those are equally just 24 possibilities if they're all equally likely. I don't know how you read a die like that. Like, how do you even know what the top is?
There's a flat side. The 20 would be.
Oh, no, I understand that, but I mean, wouldn't there be other sides that are kind of almost flat, or 20-sided die?
You just read the one that's the most at the top.
Okay.
But I usually just play.
But you actually see better than I do.
I play online, so
Okay.
it just tells me a number.
See, I'd be better with that. I'd be better with that. Here's an example. Number of goals scored per year by a hockey player named Mario Lemieux, who I consider to be the best hockey player in the history of the sport. There he is there at the 2002 Olympics, where we won the gold medal for the first time since 1954. So here are his goal scoring totals. You should know that a lot of goals in an NHL season is, a benchmark is 50. That's considered superstar kind of status. The most ever scored in a season is 92. Okay? So here are his seasons. Now here he's 18 years old. 43, 48, 54. Oh, he's got a couple good years there. 45. It's weird though, what happened here? And here, he got hurt a lot. His career ended prematurely. He actually did a comeback after he bought the team he played for. So he came back and he played for the Pittsburgh Penguins, and he owned the Pittsburgh Penguins at the same time. It was because he was owed a bunch of money by them, and he said, okay, fine, don't pay me the money, I'll take the team. So for a long time, he owned the Pittsburgh Penguins. So he was being coached by a guy he could fire, which I thought was fascinating. And he played up until 2006, but he had he missed like 4 years, he retired. He also missed time. This year, which one is it? Probably that year there, with 35 goals. He missed 6 weeks due to cancer. He had cancer, and he came back after 6 weeks and still won the scoring title. He's a very special athlete, This year here, where he suddenly scored 70 goals, he was asked, why did your goal production go up so much? He said, I quit smoking. That's it. Hell of a hockey player, okay? So, the nice thing is, the reason I use Mario is partially because I think he's a great player, but also partially because there's all these weird little anomalies in his goal scoring totals. And we can look at those anomalies and they can tell us a little something. Where did I put my mouse? There it is, okay. I'm using an iPad to control everything. I can see that better. So a histogram would probably be a good start, but we're gonna probably want to group the values. But we can make a histogram. We got numbers here. And you put numbers into Excel or whatever, and it'll give you a histogram. Right? So here's the histogram. So this is just number of goals per season. Now, look, again, I'm doing this for myself, not to present to anybody. I realize I'm presenting it to you guys, but think about this, that I'm presenting it to myself. I know there's no such thing as playing officially 2.5, 3.75, or whatever time seasons. That doesn't make any sense. There's 1, 2, 3, how many games? It's a season. And we've got a bunch of things that are grouped together here. So we've lost richness in our data here. The original numbers are gone now. We got a bit of a feel for it, but the numbers are gone. You also might wonder, 90? I don't think he ever scored 90, did he? 85 to 95. Actually, 84.5 to 94.5. It fits in there. What's happened is the computer has picked these numbers, and the computer said, oh, round numbers are nice. We'll give them round numbers. So actually, this 90 is the midpoint. It's 89.5. I think it's 89.5 to 94. No, 89.5 to 99.5. All right, or something like that. 84.5 to 95. 94.5 actually. I got it written right here. Yeah. The midpoints are, why do I have five? That's obviously a mistake. Oh yeah, so 5 to, yeah, that's right. 5 to 14, 15 to 25, 25 to 34, etc. Okay. This is one of those things we used to really harp on this a lot. I remember in grad school getting students to make graphs and tell me what the midpoints were and the limits were, and really a computer will just do it for you. And it's not, you don't lose a whole lot having a computer do it for you. So have a computer report do it for you. That's the real limits, as I said here. Don't worry about that. It's not something to get worked up about. The important point is, this gives us an idea of, he was typically at least a 50-goal scorer, and he had a couple of weird years and a couple of crazy years, like crazy good years. I mean, they were all good. I haven't told you how many games he played each year. There's a lot of those years there where he played, 40 games and scored 40 goals. Mario Lemieux is a special hockey player. All right. You have to make sure the scale makes sense. This is one of the things that, this can be a real issue. Markers in here, are there? Nope, I'll have to remember to bring some later. Do we have any up here? There's no markers. That's okay. I can do that. So the y-axis basically is an important one to be a sensible scale. So if really easy, better if I could draw this thing. One of these. I don't even know what this is. What even is this? Anyway, it doesn't matter. Shiny object. Let's say you were comparing the price of two objects. How much it costs? Yeah, let's do this. So when I lived in Newfoundland and Labrador, a very common way for people to heat their homes was with oil. There isn't natural gas there. It's weird. They have it. They ship it in. So it's oil. A lot of people use wood, and a lot of people use electricity. So the oil company was trying to get, the electric company was trying to get people to switch from oil furnaces to use electric heat. And they're saying, it's constant, all this good stuff. And they said, and it's not any more expensive, or it's not very much more expensive. And instead of showing the bottom of the graph, the origin as being 0, because if it's 0, I can look and go, how much is twice as much, 3 times as much, etc. It started at $50 a month, or something like, or $100 a month, and then just went up to like 125. And it's like, it looked like there was hardly any difference. And it looked like that because of the scale of the y-axis. It was being misleading, and they were doing it on purpose. You will see politicians do this a lot, of all political stripes, when they're talking about things like unemployment or economic data. They'll do things like this. Just keep an eye on it. You have to really watch this. Computers typically will be sensible when you ask them to do this, but always double check. It's always important to double check that there isn't some kind of problem. Whoops, there we go. So with group data like this, you'll lose, as I said, the richness in the data, which is okay with a big data set, but maybe not here. Here I think we have so few numbers that we wouldn't probably want to lose those numbers. If we've got hundreds and hundreds of numbers, hundreds and hundreds of numbers, a big batch of numbers doesn't help anybody. Here we had, what, 14 numbers or something. It's not that bad. Maybe we can still keep this, keep all the numbers, keep the richness in the data, as I say, but have some way of visually kind of summarizing it. And of course, obviously there is something, or I wouldn't have a next slide, which is a stem and leaf plot. Now I know you've seen all this stuff in 2126 before. You may have even seen very similar slides to this. Because in 2009 or 2010, when Dwayne got here, I gave him all my slides from 2126. So you may notice some of these and think, I've seen things like this. They were tweaked a little bit. I think Dwayne's example is golf. I use Mario Lemieux. Here's a stem and leaf plot. Here are the stems, the 0 to 8. Here are the leaves. And I've put them in order. This is an ordered stem and leaf plot. 3, 4, 5, 8. See, 1, 6, 7. That's the order part. The leaves are ordered. Okay? This is an ordered stem and leaf plot. You interpret this like a histogram. In fact, you turn your head sideways, it looks just like the histogram looked. Right? It really does. It's exactly the same peaks, and there's one big one in the middle. Beautiful. Looks the same. It's easy to spot outliers. Now, you might say, Dave, what's an outlier? You will see technical definitions in textbooks. You know what? It's a weird number. That's all it is. It doesn't belong. There really isn't an accepted definition of outlier. An outlier is just a weird number that doesn't belong. So you might look at this and go, he scored 1 goal one year? Yeah, that's one of the years he played like 6 games. I think that was probably his last year. Yeah, so he ended up, he owned the team, and then when they drafted Sidney Crosby, he said, well, Sid can come live with me. And they got to play together for a year, which was pretty special. It preserves the data. I can get all the numbers back. I'm assuming the right numbers and I copied them properly. Perhaps I didn't. If there is a discrepancy, that's just a copying error. There's nothing magical happening. It's easy to get the middle value, or 50th percentile, which is 44 in this case. Well, how many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There's 17 numbers. So if I go 8 on either side, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Ah, yep, 44. That's the middle. 50% off, the median. It's all those things, because those things all mean the same thing. So it's the 50th percentile or the middle. Okay. 50th percentile just means it's 50% of the data fall below that number. Okay. So a lot of you, I think some of you at least, will apply to graduate school, will probably write the graduate record exam, the GRE, and the GRE, you'll get a score, but the score doesn't matter. What matters is your percentile rank. It matters how you did relative to everyone else who wrote the test that day all across the world. So I don't know my GRE scores, but I know my percentiles. I know all of them still. Because I'm weird like that. Right, so you want to be up in the high. We can actually get something to describe a batch of numbers called a 5-number summary. The 5-number summary is something you can actually also get from the stem and leaf plot. The first thing you get is the median. Well, we came up with that. Remember, the median was 44. Now, the first quartile and third quartile, or the 25th and 75th percentiles, they're basically the median of the first half and the median of the second half. And I've read them just right off the stem and leaf plot. Okay? This is one of those things, too. You'll see formulas for this. I don't need a formula to go 1, 2, 3, 4, 5, 6, 7. It's just this count like your freaking finger. Don't make it more complicated than it has to be. Seriously. So halfway between the minimum and the median and the maximum. And obviously minimum and maximum, you know what those words mean. I'm not defining those. Biggest and smallest. Okay. Questions so far? No one's had a question. So far you're wondering, A, what's that noise? Because we all are. And B, this all seems really easy. Because so far it is. I hope, or you're all completely lost. That's also possible, that you all seem to be writing things down, so I don't think you're lost. And I don't sense the lost looks on people's faces yet. I say sense because I can't see them, I just gotta feel them. Little blind jump there. Small, obviously, got no laughs. Small, a little smile, that's what I'm getting. Okay, that's called the 5-number summary. It gives us just a very broad idea of our batch of numbers and what's going on in it. Okay? Yeah, the minimum and the maximum. So our minimum was 1. 1 year, Mario only scored 1 goal. And 1 year, he also scored 85. What a special hockey player. So, oh, by the way, that gives you the range, 85 and 1. You'll see the range sometimes written as 80, in this case 84, and sometimes you'll see 1 to 85 is the range. Both of those are fine. You can now take the 5-number summary, and you can make a little something called a box and whisker plot, which the cutesy names, I don't know, stem and leaf, box and whisker. Are we trying to make it like your children? I don't know, but that's what they're called. I like calling it a box plot because it sounds a little bit more serious. Box and whisker is fine. You don't see these a lot in presentations or articles, though you're starting to. I think this stuff is finally, after all of these years, people are finally realizing that, looking at the actual distribution of numbers is important. So I'm starting to see these in talks, especially. When I go to conferences, I'm starting to see box and whisker plots. So I'll show you a box plot right here. So here's one now. How did I do this? I think I went into SPSS and put the numbers in and selected box plot. Look, minimum, maximum, median, 25th percentile, 75th percentile. This is telling us that most of the data are in this box. Now there's a couple of ways of making these whiskers, as they're called. I've made them going just to the extremes. And that's one way. The other way to do it is make them have 1.5 interquartile distances. The distance between the 75th and the 25th percentile is called the IQD, or interquartile distance. Quartile, Q-U-A-R-T-I-L-E. Okay, so it's the distance between here and here. And then what you do is you multiply that times 1.5, and that gives you your 2 whiskers. Why did I not do that here? Well, I didn't do it here because if you look, I have to go below 0. You can't score fewer than 0 goals in a year. That's not a thing. So it would be meaningless, right? You can't score fewer than 0 goals. So that's why I just did it this way. I went minimum maximum this time. That's a choice I made. Again, this is something, for me, it's not something I'm using to present anywhere. So I'm just concerned that I can understand it. But I think you can also look at this, and I can pretty easily explain this to you, minimum, maximum, you get it. There is a video on the LMS about how to make a box and whisker plot with PSPP. So you want to check that out. As you can see, I run out of ideas for titles, so I'm just going to say, and it continues. Right, so we've talked about central tendency of distribution a little bit. We can see that, we get the medians, part of that. That's one of 3 properties necessary to describe the distribution because we need the central tendency, the spread, and the shape, right? So we can also talk about shape, kurtosis, and all that other crap that I can never remember what it actually means. But what we want something to do with also the central tendency. We want to know the mean, the average, the most common number. One of those, maybe all of those would be nice. All right. So as I said, we can also talk about shape. Here's an example. So consider this batch of numbers. 5 numbers, 1, 5, 9, 20. 20, 30. 1, 5, 9, 20, 30. I don't know what these numbers are. I am not a very creative person. They're numbers. I don't know what they're measuring. Here's another batch of numbers, 11, 12, 13, 14, 15. Okay? There's just two batches of numbers. I don't know what they're measuring. Make up your own example. So, they both have the same mean. If you add them up, you get 65. You divide 65 by 6, by 5, and you get 13. So they both have the same average. They have the same mean, which is what that is. Right. But they're obviously not as spread out as each other. And they're not the same shape as each other. Well, shape-wise, they're both uniform, so okay. Because, you know, you get a 1, a 5, a 9, a 20, a 30, or an 11, a 12, a 13, a 14, and a 15. So, as I say here, these numbers, they're the same, but they're different. It's like they're the same numbers, but they're different. So there's our batches of numbers again. So they both have the same mean. They're both symmetrical distributions. So the shape-wise, they're the same. But they are not nearly the same as when they're spread out they are. Their spread outedness is how they're different. Right? The one on the top is much more spread out than the one on the bottom. Much more. All right. So one on the top's a lot more spread out. Sort of one of the, yeah, it's more spread out. So we have to find a way to measure spread outedness. Right? Now, we could just, there's a lot of ways we could do this, by the way. We could use the range, I think I mentioned before. We could, as a start. It's not going to tell the whole story, but it would give us something. We had what? So it's 9 to 30, and then what? 11 to 15 or something like that. That gives us an idea that one's more spread out than the other. Okay. All right. Let's start. Obviously, we're going to need something better than this. So 1 to 30 versus 11 to 15, or we could call that 29 and 4. Either way, it shows us, we can see that one's more spread out than the other one. It's pretty crude. Really, it's a pretty crude way to measure this. I mean, it's a real thing, but it's crude. We could look at the interquartile distance. So the distance between quartile 1 and quartile 3 are the 25th and 75th percentiles. We could. That's a little bit finer grain. Now, with 5 numbers, it's not going to help us a whole lot. But that's, again, it is also a measure of spread outedness. So that's just the 75th minus the 25th percentile. Again, as I said, it's still a pretty crude measure. The weirdest thing is, what's this? I don't know. Sometimes, like, weird things just are in classrooms, and there's no idea why. I found an umbrella once. And as the term goes by, stuff, like, there's a plant here. I'm not opposed to plants. But why is it here? Is it fake?
Yes. I hope it's fake. There's no windows in here.
Yeah, it's fake.
There's been some classes on the first floor that have had with no windows.
Or fruit plant.
It's fake. It's fake.
No sun for you.
So that's why everything I try, you have to give them sunlight. Write that down. Anyway, again, still pretty crude. We need something better. And we need something kind of like a mean, something that gives us a number that is like the average spread outedness. That's what we want. That'd be great. Average spread outedness. And I know you all know this is going to be a dead end, but I remember thinking about this in intro stats and think to myself when we were going over this and thinking, well, why not just do that? Let's get the average. That's what I did here. So this is the average deviation. So we've got, and I'm using the 11, 12, 13, 14, 15 data set, and we know the mean is 13, 1 minus 13, and 5 minus 13, and 9 minus 13, and 20 minus 13, and 30 minus 13. So that gives us 12 minus 8 minus 4 plus 7 plus 17 over 5, which is nothing. Oopsie. I think you can probably see that it will always be 0 in this quantity. Unless you've made a mechanical error, it has to be 0. Because it's looking at how different something is from the mean. That must be 0. It's going to always sum to 0. Because when you think about it, the mean is like a balancing point. So if you think about a function, so a graph, a function, an equation, as being a thing, and it's got density, okay? And the density is the stuff underneath the curve. So you have just as much on one side as the other. That's where the mean is. So it's kind of like, there's never like rulers anywhere. But if you ever done this, take like a yardstick on your fingers and you just go like that, and eventually you'll get to the middle. You can balance it on your finger because there's just as much weight here as there is here. That's really the mean. That's exactly what this is. This is telling us we should have, this is frankly saying, of course it's 0. We should have just as much deviations from the mean from one side as we do from the other side, because the mean is the balancing point. This then makes this quantity, well, it's always going to be 0, and if it isn't 0, as I said, you've clearly made a mechanical error. Now, you might say, well, Dave, I would never obviously do this because 0 is not going to be a very useful number for me. You're right. So we have to get rid of the negatives. How do we do that? Well, do you remember in about grade 7 when they told you the absolute value and you said, I'm never going to use this? Ha! You're about to. Yeah, absolute value. So absolute value is just the size of the number minus, get rid of the sign, no sign. So I did it here. Look what we have. So just taking the absolute values. Sum of the x, sum of, you know that symbol, the summation sign? Sum of the x's minus the x bars divided by n. 1 minus 13, 5 minus 13, 9 minus 13, 20 minus 13, adds up to 48, divided by 5 gives us a number 9.6. That actually feels right. Look at the numbers, like, I don't know, remember the mean's 13, we got 1, 5, 9, 20, yeah, the average, it's almost 10. Okay, that's a quantity that we can calculate. Yes, it is. It certainly is a quantity that one can calculate. Don't get too worked up over calculating it. It's one of those things one never calculates because it's pretty much a dead end. But theoretically, it's got, I think, some value. So at first this seems, where am I here? Here we go. At first this seems pretty cool, but it isn't. This is called the mean absolute deviation, MAD. It's a real quantity. Like, this isn't something that I just came up with and said is a piece of crap. I'm telling you this is a real statistic. It just is hardly ever used in statistics that anybody finds useful. But it's real. It's a real quantity. And actually, on its own, is fine. It's just that it doesn't fit with a whole bunch of other statistical methods that we have developed over the last 150 years. So it has its use. Its use is not really in a class like this, unfortunately. It's a quantity, and one can calculate it. Sadly, it's a dead end. I say sadly because it's easy to calculate and intuitively pleasing. Right? Like, intuitively, it just makes sense that it works like this. I remember, again, when we were learning about standard deviation in my intro stats class, in 1985, Jesus Christ, learning this stuff and thinking, oh, I bet we're just going to take the absolute values. And you might even think of the same thing when Dwayne went over this stuff with you guys in 2126. And of course, you find out it's dead. It has real intuitive appeal. It's a real shame. Like, it makes sense to me. It makes complete sense to me. Unfortunately, it doesn't matter what makes sense to me. All right. Questions so far? Anything?
Why doesn't it make sense?
So why is it useful?
Yeah.
There's a very deep answer to this. Okay, all the calculus that all this stuff is based on figuring quantities like this out a different way. All the calculus that this is based on squaring the numbers. What I'm saying is that and I realize it may not be an entirely satisfactory answer, but what I'm saying is that it works with everything we're going to do, which is kind of circular. I understand that. But those kind of statistics allow you to make precise estimations, so point estimates. The kind of statistics you can do with mean absolute deviation, which you can, don't allow you to make inferences about a population from a sample. They're non-parametric. So they tell you about the sample, but that's it. We want to find things that we can take a sample and say, this is how the population works. This quantity doesn't allow for statistics that do that. That's what does that help? Make some sense?
Doesn't give an explanation of the population, about the, like, interpretation?
Yeah, so you can't, so when we calculate, well, I mean, you know where this is going, we're going to standard deviation. We use standard deviation, we can talk about the whole population. We have beautiful things like the central limit theorem, which allow us to make guesses about the population without really knowing anything. But it's all done with standard deviations and variances. Mean absolute variation doesn't do that. It doesn't estimate a parameter. It just talks about a sample. And we really mostly just care about the universe. We don't really care about samples. We want our samples to be good, but we want to be able to talk about the universe, not just the 18 people in our experiment or the 5 chickadees we're testing. We want this to be about to be able to generalize to all of them. And statistically, we can only do that if we do statistics that have that use squared quantities. Yeah. So just when I say it's a dead end, it's like that's about this set of numbers and nothing else. That's why it's a dead end. Whereas other standard deviation and variance are about these numbers, but also they apply to all the other numbers too. It's more versatile. So there has to be another way, and of course I've spoiled it already, but it was already spoiled, and also I don't believe in spoilers. I think that's crap. It's so tired of that. Spoilers! Anyway. Okay, how do we get rid of negatives? Well, square the deviations. Because, minus 4 squared is 16, same as 4 squared is 16. Right? So, good. We'll just square the deviations. That gets rid of negatives because with real numbers, right, you can't have squared quantities are always positive. Right? You can't come up with a negative number. So, like, negative 5 times negative 5 is 25. It's not negative 25. Right? And then it gets confusing when you learn about imaginary numbers. Imaginary numbers in school. I. The square root of negative 1 is I. The weirdest thing is that you might think somebody just thought that up because they were high or something, and actually it's totally useful in electronics. So, like I said, negative 9 squared is 81. So it's 9 squared. Beautiful. Let's square them. That's what we're going to do. You know we're going to do it. Let's do it. Here it is. So, x minus x bar squared. So x minus x bar squared over n. So far right now it's going to be over n. So it's going to be negative 12 squared. So that's going to be 144, 64, 16, 49, 289. Put those together divided by 5. We got 112.4. This also used to be one of those things that was pretty easy to do because old people like me were taught how to square numbers in our head. Like we were told to memorize the squares of all numbers up to 25, which is something we were taught.
I don't know why they stopped teaching.
I don't
that.
either.
I feel like it would be.
There's all
useful.
kinds of things they stopped teaching you guys.
I know.
I'm not saying that it should always be like it was when I was little, because it shouldn't. But things like memorizing your times tables, memorizing the squares of numbers, those are useful things.
My teacher saw me do it, but it was because I was always finished my work before
No,
everyone
but
else.
then-
And
well,
then they
good for
realized
you.
they were like, oh, you're done. We're gonna give you more
Well,
things.
good for
than
you,
everyone
I'm
else is
glad.
doing."
But yeah, it doesn't happen as often as it should. And then people get amazed, I go to the corner store and I know what the tax is on something. And I've got the arithmetic, and they're like, how do you know that? It's like, it's 13%, I did it in my head. What are you, Rain Man? It's not that hard to do math in your head. Arithmetic, math's a little harder. Anyway, this is easy, look at that. That's a weird number, 112, that's big. That's really big. Well, obviously it's a square quantity, we're gonna take the square root of this. Right? So they're squared units, you know. Just like if these were all heights, these are now areas, we've squared them. So let's get them back to original units, we're gonna take the square root. Opposite of squaring something is taking its square root. Okay. A little squirt. So you take a square root and you get the number. In our case, it's 10.6. They teach you guys to learn to read with phonics? Like to sound out words?
They didn't do a whole lot for us. I can't remember. I'm 26, and I can't remember what we did.
That's okay. That's okay. It probably wasn't very good then.
The most memorable thing I remember was them taking out cursive and then putting it back in.
Yeah. That doesn't bother
No,
me.
they took us
That's not as big a deal. I mean, that's fine. I can read it and it's not hard to learn. It's the kind of thing, if you had to learn it, you could learn. It's easy.
Yeah.
I went my kindergarten and like JK. I did. It was kind of like French immersion, but it was Ojibwe immersion. So I'm like,
Okay, cool.
no clue.
Well, at least there's still, some of these things, they're the only language. So. But yeah, phonics, right? So in that case, how to get, did you learn like this letter makes this sound, so it sounds out that word? That kind of thing? Yeah, well, then that's
I
phonics.
think they're doing that right now.
They're-
because my daughter's in kindergarten, like
Good.
JK. So
Good,
they're
they'll
doing
actually teach you, she'll learn how to actually read.
I think they took it out and then they went back to it because they
Yeah.
were like,
Yeah, that's what happens.
Yeah, they don't release EQA homeworks anymore because of how bad our province is doing. It's that bad.
Well, also, standardized tests are stupid.
Maybe it did do phonics.
That's right.
All right, there's a problem here, and the problem is, and I know you know this, is that it's got N on the bottom, right? And that's going to be a problem because you know that it's not supposed to be N. And I know it also just makes sense that it should be N. But it isn't. Okay, so if it's N minus 1, well, let's, in fact, if it's N, we get a biased estimate of, this is why we care about this, and this goes back to what you asked, okay? We're trying to make, we get estimates of these values in the population. If we're gonna do that, we have to divide, we want an unbiased estimator. Well, when you divide by N, you get a biased estimator. Okay? What happens is it underpredicts the size of the standard deviation in the population. The cool thing is we know by how much. So we can look and go, oh, if we just subtract 1, we now don't have a biased estimate. And N minus 1 is the number of degrees of freedom the numbers we have, the numbers we develop have, okay? So they have degrees of freedom. So the numbers can vary. This is a really strange thing to think of, because right now you have to think about numbers varying without knowing that they're doing it, and the numbers don't know where they come from. The numbers have a variance, a standard deviation, a mean, but we don't know what the numbers are. But we know numbers that describe the numbers. So if we know what the standard deviation is in population, we can then, and we know what it is that, sorry, let me back up. We can calculate it from the the sample and then estimating the population. We divide by n minus 1 because we have n minus 1 what are called degrees of freedom. Think about this. If we have our 5 numbers had to add up to 65 to get a mean of 13, right? So if we took, let's just make up some numbers. And this is easier to do with a marker, but I don't have one. Give me a number.
10.
That's a good one. Let's start with 10. There's the first one. Give me another one. 13, that's a good one. So now we're at 23. Give me another number. 73. I just did that one. What did I say? We were at 33? 23? So 73. So now we're at 96. And another number, let's go with 0. That makes the math easy. Now we have four numbers. We need a fifth number, but it's fixed. It was at 93, our total had total 65. Our next number has to be minus 18. It has to be. It must be. It can't be anything else. Assuming I did that correctly. Maybe 23. Yeah, doesn't matter. Point is, it has to add up in that case to 65. Right? There is a restriction on the batch of numbers. And you're thinking, Dave, wait a second. No. When I get a batch of numbers, it doesn't have a restriction placed on it in the beginning. No, you're right. No, it doesn't. But when I say I'm calculating it from sum of the x's minus x bar squared, you fixed a number in there. You fixed x bar. You said that's the mean. You did it, not me. Well, no, the universe did it. This works like that. So what happened is, this number is fixed. The x bar, we have fixed the quantity, we lose a degree of freedom. We lose a degree of freedom. Which reminds me of my stats prof in grad school, Ian. You'll hear a lot about Ian because the way I think about statistics is all because of him. And he said there's one statistics joke, just one. And these two unbiased estimators run into each other at the bar. Obviously, it's a bad joke. And one says, how do you like being married? And he said, it's fine as long as you don't mind losing a degree of freedom. So it's not even funny. And that's the closest thing to a stats joke. It's not funny. Statistics isn't funny. It's just not funny. So we want to estimate this thing in the population. How are we going to do that? We lose a degree of freedom. So the population parameters are what we're trying to estimate. The sample statistics are what we measure. Okay? So the population parameter, variance, and standard deviation have big N on the bottom. The sample statistics estimate use little n minus 1. Big N means population total, in this case. Little n means sample size. If they had n, they would underestimate the population parameters. And we know by how much, so we just lose a degree, lose a degree of freedom, and everything works out just fine. That's the beauty of this stuff, right? So, here are our sample statistics, right? They're pretty. S squared, that's standard deviation squared over variance, equals the sum of the x's minus x bar squared over n minus 1. And then to get the standard deviation, you take the square root of that entire quantity. Okay? The square root of that entire quantity. So it should tell you something. These values will always be positive. They can't be negative because they are all based on squared values. They must be positive numbers. And that's going to be helpful to us when we sort of derive some of the stuff as we go along. They must be positive numbers because they're squared quantities. Okay? So any variance or variance estimate has to be a positive number. It cannot be negative. Variance cannot be negative. It is literally impossible. All right. Any questions so far? I think this is actually a very sensible place to stop, even though we aren't really done with our time yet, and that's because I know that this stuff gets intense and you haven't done this in a while. So we're going to stop now because I know nobody likes this. Okay? So we'll stop now. We'll continue talking about this next time. Okay? All right. I'll hang out a bit if anybody has any questions or anything, and I'll see you next time. The important thing is I figured out how. Okay. So last time we were talking about different ways of measuring spread outedness. The ways of measuring spread I like spread outedness, that's fine. And the one we came up with, that we derived, that was the most useful, was the sample statistic here of standard deviation, which is the sum of the x's minus x bar squared over n minus 1. We take the root of that. And the variance, of course, is just that thing squared. Okay? Remember, those are sample statistics. The point of those things is to estimate population parameters. And I was asked the other day about, well, why is something like mean absolute deviation useless? It's useless because it doesn't predict anything in the population. It just talks about the sample. This talks about the sample, and then, because of the way math works, allows us to predict the future. Or not predict how it's not the future so much, just how a population will score on some metric, on some variable. Okay? Right. So in our case, in fact, if we did it and we divide by n minus 1 instead of n, we get the number, at the end, the number we get for standard deviation is 11.85. And if you look at those numbers, what were they again? That's our bigger, yeah, that's the ones that have more spread, 1, 5, 9, 20, and 30. Gee, 11 seems like a reasonable kind of amount that they're, 11.8 is a reasonable amount that they're out from each other. I kind of like it, it's fine. It's really fine. Intuitively, it's a little weird with the n minus 1 on the bottom. But like I said, if we use n on the bottom, we end up underestimating the population parameter, and we know by exactly how much, which is really nice. And we can fix that by subtracting 1, by subtracting the amount of degrees of freedom we've lost. So again, I did this the other day, but I didn't have a marker handy, so I couldn't actually do this on the board, but I can show you this. So these numbers, remember, they had to add up to 65, right? So if we just picked some numbers, and it was like 7 and 3 and, I don't know, 9 and minus 10, and it's going to be 5 numbers. Okay, so then our final number, these have to add up to 65. This adds up to a 10, so 9. So we need to get 56 has to be this number, because that's what's going to add up to 65. It's fixed. When we fixed the mean, you say, what do you mean we fixed the mean? We calculated the mean. The numbers don't know we calculated the mean. The numbers, in the numbers perspective, we fixed something. We said, that's a restriction. Okay? And the restriction is the thing we estimated. And what we're estimating here is the standard, is the mean. To calculate this, we had to estimate something. What we estimated was the mean. Okay? That's the statistic that's in there. Questions? Does that make sense so far? Okay. Those of you watching the YouTube video, notice how the beeps have stopped. I'm tempting fate, the beeps may start back up again. Please do not start back up again, beep gods. I assume it's a god letter. The beep god. Okay. So for the population, things are different. For the population, first of all, they're different because we use parameters. Population, parameters, sample statistics, P and P, S and S. They go together. It's easy to remember. We use Greek letters for parameters. So we have sigma squared and sigma rather than, and you know what the worst part of this is? This little thing over here on the left, that's a small sigma, and that's a capital sigma, the big one there. So the capital sigma means something different from the small sigma. And you'll find out as we go through the course, different letters and symbols they sometimes mean different things in different contexts. Okay? Sigma squared equals sigma times x, big X. Those big X, that's it. Whoops, that these are actual population values minus the population mean. See, to calculate this, you haven't fixed anything. The mean is actually a characteristic of the population. Because it's a population parameter, mu here, unlike x bar when you do a sample, is a characteristic of the population. It exists, independent of having to calculate it. Think of it that way. Whereas to get x bar, we have to calculate it. So big N here for population size. So these are characteristics. Population parameters are characteristics of a distribution, characteristics of a batch of numbers. That's what they are. Okay, they're characteristics. They are not things that are calculated. They just exist. We can describe them using calculations, but they actually exist. Whereas if we're calculating the mean of a sample, the point of that is eventually to estimate a population parameter. Okay. So for these, we haven't estimated anything. So we don't lose a degree of freedom, so we use big N on the bottom. All right. So those are population parameters. And the sample statistics are unbiased estimators of these population parameters. Okay. So how are the variance and standard deviation affected by extreme scores? Okay, well here's our data set, if you want to call it that, of 5 numbers we've been playing with. As I tie up my shoe. So 1, 5, 9, 20, 30, so ones we've been sticking with. Standard deviation there is 11.85, we calculated that before. Okay, let's throw a new number. I don't know, 729, I just picked the number. Now what happens? Well, it's going to obviously make this bigger. So 1, 5, 9, 20, 30, 729. That's obviously going to affect the mean, isn't it? It's going to get a lot bigger. If the mean gets bigger, it's probably the case that the top of the fraction gets bigger, right? Our new mean is 132.3. It's way bigger. Because it was, what, 13 before, I think? Or 12? 13, I think. Yeah, 13. Our new variance is 85,555.067, and then the square root of that, which I'm sure you all know, is about 292.5. So our standard deviation was heavily affected by an extreme score. One extreme score. Now, that is, of course, one of 6, but it still affects it. Right. The mean is affected by extreme scores. The standard deviation depends on the mean. Therefore, standard deviation is going to be affected by extreme scores. Note what would happen here with the median. Not much. Would hardly move at all. What is it right now? It's 9 in the top data. Sorry, yes, it's 9 in the top data set, right? It's the middle number. Now the middle number is 20. It hasn't got up that much at all. So when you're comparing two groups on some variables, very rarely do we do this in psychology, but we might sometimes if we have a variable that's very affected by extreme scores. You will, however, see this done. Pay attention to any labor negotiations. Labor negotiations are great for using means rather than medians. Right? Like, think about this. This is what, about 70 professors, something like that. Let's pretend that, I don't know, let's pick somebody. Let's pretend Paul makes $7 million a year. He doesn't. At least, I don't know what the rest of his financial, I know how much money he makes. It's a matter of public record. It's not $7 million a year. But if that was the case, that would really pull the mean up, even with 70 people. It would hardly touch the median. So a lot of times, then let's say we were on some kind of labor dispute, you would probably hear the administration talking about the average salary. Maybe putting Paul's in there, and we'd be going, what about the median salary? Most of us aren't the rich guy. In fact, he's the one. Right? They're both valid measures of central tendency, but they're affected differently by extreme scores. Okay? So it's just something to consider, to keep in mind. All right. Questions so far? Boy, the lack of beeping is so refreshing. Okay. So how can we use this knowledge to our advantage? Well, if we're doing exploratory data analysis, there is a quantity we can calculate called the coefficient of variation. Slow, eh? Here's some data from Katz et al. 1990. I believe these data are actually in the book, so you can take a look at that, at least in the discussion of this study. And what happens in this group is we have two groups of people, and one group has studied before a test, and one group has not studied. Okay? So one group has a mean score of 69.6 and a standard deviation of 10.6. The other group has a mean score of 46.6 and a standard deviation of 6.8. Okay? And these are actual real data. These were collected. This is kind of weird, isn't it? One could kind of conclude here, just looking at this, that there's more variation than deviation when you study. That seems strange, doesn't it? You would think that it would get, you'd tighten up, you get a little bit better, you get more similar performance among students if people studied. But that's not what this seems to have found. What the hell? That's very strange. It's a very strange result when you think about it for a second. It's like, this makes no sense. Well, let's remember that the coefficient of variation, which is just the standard deviation divided by the mean, this divided by this, and this divided by this. What that's doing is it's correcting for the fact that as the mean gets bigger, the standard deviation gets bigger. So what we've done here is I've just compared two coefficients of variation at 0.152 and 0.14, so they're almost the same number. So in fact, these aren't any more variable. This number's bigger, 10.6, because 69.6 is bigger than 46.6. That's all it is. And again, this is something you would probably only use in exploratory data analysis. It's unlikely that you'd share this in a paper. You might. You might. Questions on that? Does that make sense? It's just a way of correcting for the fact that as the mean gets bigger, the standard deviation gets bigger. Okay? All right. Okay, very good. So we want to learn about populations, not samples, but we don't have access to populations. We have access to samples. So we estimate population parameters using sample statistics. But we don't really care about our samples. I mean, we care that they're good samples. And you've all taken 2127 and 3286, I think probably most of you, so you know how to do that. Different class. But we don't really care a lot about our samples. We want unbiased estimators of population parameters. Okay? So the mean is an unbiased estimator. Oh, good, there is an eraser. The mean is an unbiased estimator, like X bar. I can just write that up right here. The expected value of X bar equals mu. That's a notation, so the E with the parentheses, that means the expected value. What's an expected value? It's the value you would get if you theoretically did something an infinite number of times. Okay? So the expected value of X bar is mu. The variance of some number, X, equals that, sigma squared. So if we calculate the variance, we will get an unbiased estimator, which will be sigma squared. All that's just saying is S squared basically equals sigma squared. So what you can do then, what this knowledge tells us, what this allows us to do, is it can tell us what we can do to whole batches of numbers and see what happens to them if we play with them a little bit. So here's some examples. The expected value of x plus k, this actually shouldn't be x bar, it should just be x. The expected value of x plus k, x is just a number. It's a variable. The expected value of some number plus a k, a constant, that's going to be the same number all the time. It's going to be x bar plus k. So think about this for a second. Think about this. If let's pretend that everybody does very poorly in the course, okay? It's not going to happen. Let's pretend. I get the final marks, and the average typically in this class is around 78. Right? It's about that. You might think that seems high for a statistics class. It's because these are all people who have already taken another class, right? What if I see it's 68? I go, oh, geez, that's bad. It shouldn't have been that bad. It's never been like that. That might have been my fault. That probably wasn't their fault, because if everybody screws up, probably on me. Maybe my tests were too hard this term or something. Maybe I should adjust it. So I could add 10 to everybody's score. So it goes, did I say 68? If I go from 68 to 78 now, right? You can see how that would happen. If I added 10 to everybody's score, it's going to move the mean up by 10, right? But look at this. It says, what happens to the variance of x plus k? Well, that's going to say, adding a constant, giving everybody 10 more points. Is that going to change how spread out the distribution is? Let's think about this. Okay, so I'm going to be a distribution. Here I am. Two tails. Now, I'm going to add 10 to all of them. It hasn't changed this at all. It hasn't changed how spread out the distribution is. So the variance of x plus k is just s squared sub x. Now, it's different with when you multiply. Why would you multiply all the scores by a number? In fact, if I was going to correct marks, that's what I would do. I've curved things like twice in my career. It happens, but it's happened very rarely. But it happened once. In fact, it happened in Newfoundland. I was teaching intro psych, and I got the test back, and I was like, geez, these are bad. The average is like 50. What the hell's going on? And then I looked, and the textbook company had sent me the wrong software to develop multiple choice tests for the book. In other words, I had developed intro psych tests, but for a different textbook. Oh God, what the hell, what am I going to do? I can't make them write another test. That's ridiculous. Well, actually, the questions still are on Introduction to Psychology, and that's what this course is. They're the same topics. So there's something valid here, but the marks should be higher. Because there's stuff in there that I didn't talk about in the book that we are using, doesn't talk about. There's a few ways you can attack that, right? You can either just take out all those questions and remark them. Yeah, I'm not doing that. That sounds like a lot of work. I know what I'll do. I'll multiply everybody's score by a constant. So if the average was 50, and I want the average to be 60. 60 is fine for intro psych. In fact, it's pretty common. For your first intro psych test, average about 60. So all I did is I multiplied all the numbers by a constant, and I multiplied them by the number that would get me to 60, which would be what, 1.2, I think, in that case, right? So now I get x bar times k when I multiply all the x's times a constant. The difference is what happens to the shape, what happens to the spread outedness. If we're multiplying times a number, variance of x times k is s squared sub x times k squared, because remember, variance is a squared quantity. So it's times k squared. So all my numbers were Start doing that in your head, Dave. If I'm doing this properly, all the variance, whatever it was 14 squared. 1.96 times x. That's assuming I did that in my head properly. So all it is anyway 1.2 squared times whatever my original variance was. Okay. Now, by knowing this, you could figure out division, for example. So if I said, what happens when you divide? What happens when you divide numbers? Well, let's look. The expected value, we know that x times k equals x bar times k, right? What's going to happen if we're going to say, what's the expected value of x divided by k? Well, division is just multiplication times the reciprocal, it's pretty standard stuff. So what you get here, it would equal x bar divided by k. If you're doing division. If we did, what would happen to our variance? It's going to equal s squared over k squared. And standard deviation, you just take out the square, right? So it just becomes like 1. Or not 1, sorry. It becomes like, it's the square root. So it just s times k from the standard deviation. So the important point here is this allows us to play with distributions. And this is something you can do. You can actually move distributions around. You can multiply them times constants. You know all kinds of mathematical things to them. And in fact, if any of you who have played with assignment 1 yet know that, in fact, one of the very first things you're going to have you do is you're going to do a transformation of a set of data. There's all those data there about people's heights in centimeters and changing them into inches or whatever. I remember the whole thing. Right? Note there are a couple of videos on, or links, at least links to videos on the LMS. Those videos are also on my YouTube channel. So you can take a look at those and figure out how to try some of this stuff with SPSS without driving yourself insane. All right. Questions on this? This is the most mathy thing of the whole thing we've done so far. And that wasn't that bad, right? Multiplying times a constant, dividing by a constant, adding a constant, stuff you've done before. Remember, k is a constant, so the number doesn't change. And x is a variable. Cold over?
Yes.
Right, extra coat or something. Probably don't want to put on my winter coat, so I'm just going to leave it out there. And I'm sure you probably have one with you.
Yeah.
Yeah.
Like, I don't want to put the coat on, it might be too hot. But then
Right, it's that, yeah, you've got to find that happy medium, exactly. Right. So this, something I don't think you should get too worked up about. I think it just looks a little scary, it looks a little mathy, but it shouldn't bother you. The conclusions about this stuff, so I'm going to show you some SPSS stuff after this. We'll stop the recording, but we'll finish up the lecture part. This is easy stuff to do. Like, it's truly easy to do these kind of calculations, to do exploratory data analysis, so do it. Now, right now, you guys aren't collecting data, so it's not like it's something that you care a lot about. But when you get to your thesis next year, or whatever it is you plan on doing it, one of the things that you're going to want to do is probably do this kind of stuff to get a feel for your numbers. And I can tell you for sure that if you work with me, that would definitely be the case. I'd say, okay, show me some graphs and things. Tell me what you think happened. Then we'll analyze it later. Right? This allows you to get a feel for things. And like I said, spot some bad stuff as well. All right, any questions on this stuff? All right, so